And the other, what we're going to talk about today are these lovely Flitched beans. Sometimes they're called Flitched. Flitched, I think, means, I think you can use it as a verb, meaning sandwiching them together. So then you would normally say flitched, but a lot of people leave off the ed, they call it flitched. So you'll see it either way, flitch or flitch bean. And what they are these, like these up here, these, oops, not going right, there we go, sandwiched together with the steel. But in general, what we talk about will apply with any composite beam, basically. And there are other composites like these down here, where they've built out around a W section. And part of why you would do that, it strengthens it a bit, certainly. It also allows you to attach, if you're using this in wood construction, easily attach wood members to it then, like with hangers or whatever, or nailing. So that's another type. And then lastly, we'll look real briefly at these concrete decks that they're putting on CLT now, but that photograph is not CLT. That's just a series of members sandwiched together. A couple of years ago, one of the students, as a little test or a little experiment, made a Flitched bean, not exactly by specifications, because it doesn't, it's just done with these small pieces. They weren't even full 2x4s, it looked like. And then we bent it until we caused it to completely fail. And you can see what happened. We did put enough flexure on it that it buckled the center piece, which was very thin. I mean, you normally would not use sheet metal for this, which is what they just had on hand, so they put the sheet metal in there. And the sheet metal is much more likely to buckle, which it did. And but you kind of get the idea of it did strengthen it quite a lot, even though and it added a lot of ductility to it, even though the wood was obviously failed. It was still carrying the load. It didn't just snap, right, as wood would do. It gives it, so there's that advantage of it too, is in the failure mode, it's of course got the steel gives it that ductility that you wouldn't ordinarily have. Okay. Righty. Okay, so we'll go on with this. If my advanced works. So the way we set this up, because you've got a composite, it has two different materials with two different E-moduli. You've got to take account of that, and the theory that we follow is strain compatibility, is what they call it. And the idea is that you're going to laminate these two materials together, the steel and the wood, such that they behave together, that when you load it, they strain the same. That when you either in flexure or in compression, as you load it, the strains remain constant. So this image of the strains, this would be an axial compression, right? They're constant all the way across. They're the same strains all the way through. And in flexure, you'd have the same situation. And if they were, image that I have shows the steel on top and bottom. It kind of makes the diagrams a little bit easier to draw, actually. But even if they were at the side, the strains would be the same all the way through. But of course, they have different Young's moduluses, yeah? The E modulus is different on these two. The steel is much, much, much stiffer, higher E modulus than the wood. And so when I strain them the same, you're going to be putting a much higher, the resulting stress is going to be much higher in the steel than it is going to be in the wood, or the force. You can imagine, oh yeah, that's what I should have brought up here. Darn it. I had downstairs a sponge block, and then if you put like little shims of wood beside the sponge block and then you load it, the sponge block is carrying something, I suppose, but obviously the majority of the load is going through the stiffer material, the wood. And that's exactly what happens in this as well. The steel ends up carrying a higher load just because it's stiffer. And what you have to do is figure out what the proportioning of this load is, how much goes to the wood and how much goes to the steel. And in doing that, you have to follow the strain. So the stress in as we know is equal to the Young's modulus times the strain, right? So if the strain is going to be the same in the two materials, but they have, so here's the strain maybe, right? And if the strain is the same in both of them, but the E modulus is different, then obviously this one's going to carry a much higher stress than this one down here. So this would be probably your wood, right? And this would be the steel. So the steel is going to end up with that much higher stress. So when we do the diagrams in Flitched, say, although the strains are constant, there's a sudden jump in the stress that the steel would carry, and then it drops back down, and the wood carries, its stress. Now, when these are side by side, you just have to, you can't draw it on one diagram very easily, right? And normally that plate does go vertically in between them. It's flitched. But it would act the same way. That plate would be carrying a higher stress, and the wood would be carrying a lower stress. But they'd both be straining the same amount. They'd be working, as if they were glued together, or bolted together, actually. Okay, so the process to analyze these, this is based on Considere's law, that if you want to find the force, it's the stress times the area, and you can do it by parts. The stress times the area of the steel, and plus the stress times the area of the wood is going to add up to the total force on that member. Now we assume, like I said, that the strains are equal. So I'm thinking of this in compression now, right? That's what this is showing. But it'll be the same theory in Flitched as well. But in compression, well, no, it'll be the moment that we'd be after. All right, in axial compression, we just need the force. So the strains are the same in both of them, and the equation for the strain is the force divided by the Young's modulus. So I can say, okay, if the strains are the same in both of them, then I can write that, right? That's the same. I've just expanded it. And then I can solve for one or the other. So here I solve for the stress in the steel. So the stress in the steel then would be equal to the ratio of the Young's modulus times the stress in the wood. Okay, now I take this and substitute it back up into my Fs up here, up into that equation. And that would give me an equation that's entirely, the only unknown would be Fw. And I could solve for Fw then. And once you get Fw, then you plug Fw back up into there and you get Fs. So you find the two stresses like this, and it through the proportion of that Young's modulus. Okay. So here's a little example of how that would work out. This is with a 4x6. So this is our piece of wood here, right? This is a nice piece of wood, and steel on top and bottom. So I've got a 4x6, and this is the properties for the redwood, and a steel plate, which is a mild steel A36, quarter-inch plate. And we'll take as the compressive limit 0.6 Fy, which would be 21.6, I guess. We're assuming here that it doesn't buckle. What I'm leaving out of this, is the any instability or Euler buckling or whatnot like that. So the assumption, and for a column, that's quite an assumption, but yeah, and you would have to account for the buckling in reality, but I'm not going to deal with it right now. But and the way you might do that, you could look at the buckling of the wood member and take that CP value and apply it maybe to at least to the wood stress to reduce it somewhat. It might also, in this example, it's almost set up more for flexure. If this were, if you wanted to put the steel plates in a place that would better brace it against buckling, you'd think you'd put them on the sides here. But okay, this was an example I had, so I didn't alter it. Okay, so we're going to have a given load of 50 kips, and we want to see whether it passes or fails, right? And we've got the area. This is for our 4x6. We've got the given every time I go through these, I find some mistake. Somehow this is not EW. This is that I got the wrong one. That was F. This should be 1,000. Yeah, which is KSI. It was 1 million PSI. KSI. Okay, and the area of the steel. There are two plates at 0.875. So that's the area of that, and there's the Young's modulus for that. So okay, we're going to do the F equals A, and this will be the Fs times the A. Okay, that's an A, sorry. A for the steel plus the Fw times the A for the wood. Okay, and I solve that then for Fs, and I get that term, which I can then plug back into the Fs. So I take this term and plug it in back into that equation, and that gives me this equation, which I can then and this is the given load that I'm analyzing, the 50 kips, and we can then solve for FW. So there's the stress in the wood, which doesn't look too promising since the limit was 700 up here. Okay, so then we can back calculate the, given the stress in the wood, we can find the stress in the steel. So we plug, this is the stress we just got for the wood, and we find the stress in the steel. And you simply compare that with the limit on the steel, the allowable, and that passes, but unfortunately in this case, the FC for the redwood was only 700, so it looks like this would fail, the redwood would fail. So you see it's pretty straightforward in compression. You're just finding the that simple equation, plug the one value, in, find one stress and then substitute it back in the original equation and find the other stress. Okay, for beams it's a little bit more complicated because the stress equation is MC over I, and I is based on the assumption of a homogeneous section. That when you derive I, it's based on the constant, not only constant strain, but constant stresses through the section. So we don't have that, so we can't really use that directly, that I. So it makes it a little bit more complicated than the compression, which in A, the A we were able to use independently for each of them, and there was no problem for that. Okay, so we'll have to figure out what to do with I. But these are what they look like, the flexural members, either bolted together like this. This is probably the most common, is that right there, or scabbed on the outside, which sometimes would also probably be bolted on, which they'll do sometimes, particularly if the plate doesn't go the full length, which we'll look at in a little bit. So it's compatible with a wood structure. That's certainly an advantage. It can be nailed. They're easy to retrofit in an existing structure. So if you've got a wood framed structure and you want to change the occupancy, or you want to maybe take out a wall and have a beam in place, it's easier to scab on these steel plates or sandwich in some steel plates and add some more wood and get a strong enough member, rather than bringing in a whole separate steel W section and trying to then fit that into your existing structure. So they work better in retrofits. It's lighter weight probably than a full steel section. Certainly stronger than wood alone. You can do it with less depth than if you were using wood alone. You can get longer spans, of course, and the sections can vary over length, because the moment capacity can vary over length, because you don't have to have the steel plate the full length. You can put, if you have a beam that has a particularly high moment, like over an internal support where you have a high negative moment, then you can just put these plates just in that area, not the full length, but just where you need it. So you can optimize your strength a little like that. Okay, and of course the wood acts to stabilize that thin steel plate. The steel plate alone you couldn't really use. First off, it's almost impossible to make it stand up, but I mean, physically in construction use it, but then it would tend to buckle. You have warping just like in that little sample, even with the wood on it, it buckles. So the wood does brace the steel. Now some of the disadvantages, and this is the major one right now, it's simply more labor to make it. These used to be not too uncommon. I mean, you'd see them used in construction, but now they've pretty much been replaced. You very seldom see them because it's easier just to use one of these, particularly the glue lam. If you need the strength, you can go down and buy a glue lam off the shelf now that is probably going to do the job for you. Maybe in where you'd still see them being used is in certain retrofitting situations where I've seen I'll show you some examples where they were taking out a wall or they were doing something they needed to strengthen a beam, but the beam's already up there, and they have to keep it at the same depth that it is already. So then they'll just stab on these or sandwich in steel plates and add another 2 by 10 or 12 next to it and get the strength that they need. So that's probably where you most likely see it now.